talking about how to learn from sequence data. And again, as a reminder, we talked about RNNs, right? So we talked about the utility of the RNNs in different kinds of problems. We'll have a review of that very quickly. And also, what is the corresponding computational graphs, right, for the forward propagation, right? And we also did a little bit backward propagation to see where the vanishing gradient or exploding gradient problems might become, right? So we talked about what is the problem, why does it happen, how is it usually addressed, and why is it bad for RNNs. So I think then we should start talking about some modern RNNs, especially LSTM and GRUs, that are essentially solving that problem to some extent, okay? But again, I want to give you a reminder that, why do we care about such cases, right? So we knew that the vanishing gradient problem is that, the information from far away is probably lost in the back propagation in the gradient information, right? But that's such long-term information actually can be and can be important because, as in these cases, right? So we find out that what we need to fill in here is actually very far away. It's actually tickets, right? So in other words, there are such information which appears to be far in the sequence, but actually very close or important in the syntax. So for those kind of syntactically close, but sequence-wise far, right? So for that kind of information, if you're facing the vanishing gradient problem, then it's the last thing you desire. Is that right? So I think now it's time to think about how to address this problem more fundamentally than just try to mitigate them, right? So again, the sequential recency is not as important as the syntactic recency, which actually is sequentially far away, right? So instead of just trying to mitigate these issues, like what I said before, you can clip the gradient when it's exploding, or use some activation function, or drop out. But can we address this issue a little bit more fundamentally? In other words, you do want to consider the long-term information, which can be syntactically recent or close, but you're facing the vanishing gradient problem, right? So what can you do? So how to fix the problem for RNNs? There are a few observations. First is that sometimes an early observation is very significant in predicting future. Like that ticket was way early, right? So we need a memory, right? A memory mechanism to store such important but early information, right? The vanilla RNNs do not have the memories to keep updating the hidden states and keep some early observations in mind, right? So that's one thing, we need a memory mechanism, right? But we all know that one important function of our brain is to memorize, but another important function is that it can forget. Actually, it's a very important mechanism. And it actually helps the long-term cognition well-being. You have to remember that even though the early observations can be important, but sometimes, or many of them, are just not even relevant. So in those cases, you need to memorize, but you also have to forget, right, in the latent space, those early. So it's not for forgetting the early observations, it's forgetting the corresponding latent variables or the hidden variables in the latent space, okay? And lastly, sometimes there is a logical break between parts of the sequence, such like chapters of a book or major paragraphs. In those cases, we need to reset the internal states. So these are the three keywords, right? Memory, forgetting, and resetting. So these are the three things that are important to one of the most important modern RNNs, that is LSTM. Okay, LSTM is abbreviation for long short-term memory. Okay, so as you can see, it's trying to use a memory mechanism to use some sequentially long or sequentially far away information, right? But it's using that in the short-term way. We'll see what that means, right? So this was proposed in 1997 as a solution to the vanishing gradient problem, okay? It's not just mitigating the problem a little bit. It's a solution, right? So let's look at what the solution is, right? So on step T, there is a hidden state H sub T and a cell state C of T, right? And I put parentheses to indicate this T is the time index, right? So both are vectors of length m, and the cell state stores long-term information, right? And the cell stores long-term information, which is encoded in both. And then this LSTM as a building block, it can erase, write, and read information from the cell. Okay, so it can forget, it can add, and it can load, right? So the selection of which information is erased or written or read is controlled by 3 corresponding gates. So these gates are very important concepts. So these gates, are corresponding to these 3 mechanisms, right? So forgetting, right? Memory and resetting, okay? So these gates are of length n vectors, and on each time step, each element of the gates can be open, closed, or somewhere in between. So these gates can have different kind of states, and they are dynamic. Their value is computed based on the current context. Okay, let's now understand them in more details. So let's first look at these mathematics. Okay, so what we have is, remember, right? These gates have inputs of H and X. Remember, H is the hidden state from the previous time point. X is the state of the current time point, right? They are fed into this function, which is a forget gate, parameterized by WF, UF, and BF. Right? This is a function which is actually a sigmoid function. Remember, all gates values are between 0 and 1. So that sigmoid function is a natural choice. The second gate, so that's a forgetting gate. The second gate is to write, right? And to read, excuse me, to read. So we need to, what parts of the new cell will be written to the cell. Okay, what part of the new cell content. So in this case, again, we have H in the previous time point, X of the current time point, now parameterized by different parameters. Okay, these gate parameters are WI, UI, and BI, and then this is, the output is again fed to a sigmoid function, and so that the gate states are between 0 and 1. And lastly, we have the output gate. Okay, very similar, but now parameterized by WO, UO, and BO. So we have these 3 gates: forgetting gate, input gate, and output gate. Okay, so now that we see, right, how these H and X are fed into this LSTM building block, and now we have 3 outputs, right? And how do we deal with this, right? How do we deal with this, right? So there are 3 things to keep in mind. The first thing is the new cell content. So this is the new cell content to be written to the cell, which is a hyperbolic tangent function with very similar, input of H and X. So this is very similar format as you have seen before, but this activation function is a hyperbolic tangent. Okay, and the cell state, right? So you have to somehow erase or forget something from the last and write something from the new, right? So you have to forget something from the last, so you forget from the last, right? forget gate controls, so this is a gating function, right? So it's forgetting some of the last cell state because it's t minus 1, okay? And in the meantime, you're inputting or writing, right? This is a input gate, some new content to the cell. All right? Right? And then the hidden state is gonna be using an output gate on top of the hyperbolic tangent of this cell state at time t. So these circles, as I said, this gating mechanism is through the element-wise product. Okay? Any questions so far? Any question? Okay, so that's what the LSTM is doing. So as you can see that we have 3 gates that are basically determining, right, whose states are between 0 and 1. They're determining what previous cell state, right, what portion of the previous cell state to be forgotten, what portion of the new cell state or content to be written, and how they should be output to this new hidden state, H of t, okay? So this is what LSTM is doing. As you can see that, the way we are trying to utilize, right, this previous memory is we are only looking at t minus 1, the most immediate, the last cell state, right? Right? Because the last cell state has some memory, right? Some part is forgotten, but it has some memory from t minus 2, h of t minus 2, right? Right? So if you recall in the convolutional neural networks, we talked about the receptive field. So in that case, receptive field is talking about the spatial case. In this case, you can see that even though we are just looking at the previous state, the last cell state, but that is also determined by the previous state. So we actually have memory of the past, right? But maybe the longer ones are forgotten more, but we don't know that. Remember, these gates are having parameters to be learned, right? So it's not going to be determined by you, it's going to be learned from the data, which portion to be forgotten, okay? And now let's look at, that was just one LSTM block, right? So now, right, if you think about putting more and more into there, right, as I see, what we had before was this, LSTM, whose input is ht minus 1 and xt, right? And the output is ht, and to get this output, we actually use the 3 gates, right, determining how much of this is going to be forgotten, right? How much of the new cell states would be written, and how much their combination will be output to the next, right? So that's what we had. And we can do this in a sequential way. This is like the on-road, right? On-road recursive formula, right? Over time. Okay. Now, let's look at it again, right? So as a reminder, right? So here, as I said before, you had the previous cell state, right? And you have to determine, what portion to be forgotten, and that's controlled by the forgetting gate with some parameters to be learned, right? And then this, current state is, partially given by the previous hidden state, right? And it's going to be written, right, into the new state by using parameters from the input gate, and then we do this new cell content calculation using this hyperbolic tangent, and then these 2 pieces of information, right, the memories, right, the history information after something is forgotten, and the new cell state are put together, and then went through this output gate, right? It's again parameterized by some W's and V's, and then we have the output of the new cell content at time t and the new hidden state at time t. So this is done recursively. Okay, this is what Why it's called long short-term memory. In other words, you do have the short-term memory, right? But it's also kind of long because you have this recursive. Okay, so this is a solution, as I said. It's a solution to the vanishing gradient problem that is particularly troublesome in RNNs backpropagation. Okay? And that was in 1997, and again I redraw this LSTM, right, with the same kind of, forgetting gate, input gate, and output gate here, right? But 2 decades later, right, GRU, right, is the newer model, right, the building block. Essentially, it's less fancy and less parameters if you look at it, right? So you see that we have the hidden state, right? So instead of, here, right, we had to determine what portion to be forgotten. Here we have the hidden state, right? And then it's going to be, combined with input. Here I just want to give you a very intuitive understanding before we look at the math. And then we have a reset gate here, right? And then, excuse me, and then this is how we determine the new information, right? So apparently you see these much less parameters are being used, and then we have the output again here, right? So let's try to, compare, right? So this was in 2014 a simpler alternative to LSTM, right? So in each time step, t, we have the input xt and ht, but we don't have ct, the cell state anymore. Okay, and we have 2 gates, right? Update gate and resetting gate. Okay, and these 2 gates are taking ht-1 and xt as the previous formula, right? It's very similar. We have this linear and a nonlinear activation function. We have the u and r. One is for update gate, which controls what parts of the hidden state are updated versus preserved. Then we have the resetting gate, which controls what parts of the previous hidden state are used to compute the new. Okay, so this is the update gate, and one is the resetting gate. So what part of the current and what part of the previous hidden state? Remember, there's no cell state anymore, right? So let's again compare, right? So there's no cell state, right? So actually, I only have the hidden state from the previous time point together with the input. Okay, that's what we have. We don't have this cell state anymore, right? And we only have 2 gates, right? One is to determine how much we reset, right, from the previous, and how much we update for the current. So the new hidden state content, right, is here. It's very similar as we have before, but pay attention here, right? So we have this element-wise dot product between the resetting gates output, right? Again, these gates are between 0 and 1, right? Thanks to the sigmoid function, right? So we have these sort of the, element-wise product between the reset gates output and the previous. So we're basically determining, right? So you use this, whenever you see this circle, element-wise product, and you see this, function in front of it, or vector, which is between 0 and 1, basically what's in front of it is like a gate to what's after, right? It's like a gating the information, in this case, the previous or the last time step point's hidden state, right? So we gate the previous time point's hidden state with the reset gate's output, right? Whose parameters are to be learned, right? Then we again feed this directly to a function like what we had before. Again, w, right, times that output plus u times that output, right? So this is the hidden parameters, right? And plus bh, right? This is very similar, right? If you look at LSTM, that's what we had before as well, just right here. But we don't have cell states anymore. We directly give it to the output state. So it's like the forgetting gate is replaced by the resetting gate, and this cell state is directly replaced by the hidden state, and there's no this thing, and then you feed this whole thing and replace this part, right? So that's what exactly you get. And the output is H tilde T, right? And how do you go from H tilde T, right, the new hidden state content, this is the new content, to the current hidden state, right, so the ultimate HT, right? So essentially you are utilizing some information from the last step and some new information from the current step. Again, this is controlled by the U, that is the updating gate, right? That's right here. U, right, and this is a convex combination between the last hidden state and the current new content before we do this convex combination and call it the new hidden state. Okay? Again, how does this solve vanishing gradient problem? Just like LSTM, it's much easier to retain the long-term information, right? It's much easier to retain the long-term information, and without having to remembering everything, right? So as I said, it's as if saying that this convolutional neural network works, even though these convolutional kernels are small, they have very wide receptive field if the depth of the hidden layers is large enough, right? So in this case, using this recurrent gating mechanisms, we actually are able to combine a lot of short-term memories together into this, very remote memory. As long as it's relevant, as we will learn from the data, it will be retained, okay? Any question about LSTM and GRU for now? Any? Okay, so the LSTM, right? So the 2013, 2015, that's the time that LSTM starts achieving the state-of-the-art results. If you're going to this, this American Conference of Linguistics or other kind of NLP conferences, right? So LSTMs and later GRUs are, sort of the state-of-the-art, right? Some tasks involved includes the handwriting recognition, speech recognition, machine translation, parsing, or image captioning. These examples I have shown you before using this very simple these diagrams that we will show you again later again. And that has become the dominant approach, LSTM, okay? But since 2019, in the in the natural language processing field, actually I'm not completely thorough, because since last year, even in the computer vision field, transformers have become more dominant for certain tasks. Not all the time, so for certain tasks, right? So you can see that in this very simple example in WMT, right? It's an MT conference, machine translation conference plus competition. 2016, the summary report contains RNN 44 times. In 2018, report contains RNN 9 times and the transformer 63 times, okay? But don't get the wrong impression that, oh, we're just gonna desert RNNs for transformers, for whatever these NLP tasks are. You have to keep in mind that all of them are introduced for some reasons, and they have their own niche. They have something they are very good at. And also they are building blocks that you can utilize in your own scenery. So it's not like either this or that. If not this, then that. So there are a lot of things that can be combined together, and there are a lot of things you have to choose and use wisely. Again, we'll see a little bit more about this in today's lecture about attentions and self-attentions.